For our first example here, I want to go through a proof for our derivative of the natural log function, giving us 1 over x. With implicit differentiation, this proof is pretty nice and concise. So let's go through this. And what we're going to do is we're going to start with the equation y equals natural log of x. Now, if I tried to take the derivative with respect to x at this point of both sides, I'd run into an issue if we're kind of going with the theme that maybe we don't know what the derivative of natural log is yet. So instead, what we're going to do is we're going to change to exponential form. So changing to exponential form, just as a refresher, that would mean that y would be our exponent. We would have a base of e, and then the value that goes on the other side of the equation would be x. So what we're going to have is base e with an exponent of y is equal to that value of x. Now let's use our implicit differentiation, which our first step is to take the derivative with respect to x of both sides. So on the left-hand side, we're going to have chain rule here. So we have e raised to an exponent of y. So using our chain rule, the outside function would be that base e. So what we would have is just e and then keeping the inside function of y. And then we would be taking the derivative of y, which that would be just 1, but multiplying with dy dx. So the derivative of y with respect to x. So that's where our chain rule comes through and brings our implicit differentiation. On the right-hand side, we're taking the derivative with respect to x of x, and we just follow our rules, which would leave us with a 1. So solving for dy dx here, what we're going to have is that dy dx is equal to 1 over e to the power of y. Now what we're going to do here is use the fact that, well, we know that we said y is equal to this natural log of x. So let's bring it back to being in terms of x by going 1 over e to the natural log of x. And our exponent properties says if we're raising a base to a logarithm of the same base, they cancel each other out, and all we're going to have left over is just the value inside the logarithm. So that simplifies down to just 1 over and that value of x. So some implicit differentiation there to give us that proof for that derivative of the natural log of x. Okay, let's look at some more scenarios here. So we have an implicit equation, sine of x plus cosine of y is equal to pi over 4, which gives us this kind of cool graph over here. And how we know this is implicit, an implicit equation, is that if we're at a value like -4, what we can see are all these different spots, and they would have different slopes of the tangent lines. So we need implicit differentiation here. So we're going to take sine of x plus cosine of y equals pi over 4. And we are going to take the derivative with respect to x of both sides of the equation. So that means we'll be taking the derivative with respect to x of sine x plus the derivative with respect to x of cosine y equals the derivative with respect to x of pi over 4. Now, as you do more of these, you can skip some of these steps. I'm just going to show all the teeny tiny pieces as we go through these for the first time, but you'll need to show this kind of distribution of that derivative, but I do find it helpful just keeping things organized. Okay, so that derivative with respect to x of sine of x, so because our variables match up, we just go ahead and take the derivative of sine, which is cosine. So there we'll have cosine of x and then we're going to go plus. Now the derivative with respect of cosine y, here we're going to need our chain rule property. So outside function is cosine, so derivative of cosine is a negative sign. So I'm just going to change that to subtraction of sine, and then we keep the inside function of y, and then we multiply that by the derivative of our inside function. So we're taking the derivative of y with respect to x, and that'll leave us with dy dx. So derivative of what we're seeing there, kind of following our normal rules, keeping y as the input, but then because of that chain rule, we end up with dy dx multiplying on. And then d dx of pi over 4, so that's just a constant, so that turns into 0. And now we want to solve for dy dx. So I'm going to subtract cosine from both sides. And then divide by sine. So negative divided by negative will give us a positive, and we'll have cosine of x in the numerator, sine of y in the denominator. And that'll be our derivative function. So then we can start finding derivatives at specific points by plugging in xy coordinates. Be careful with these two because of really all of our training since we learned about functions the first time in pre-calculus. You can end up with a mixture of x and y variables, so don't assume that x is your input value. It's very common for this to change into cosine of x over sine of x. Just be careful because with these, you're going to see x and y show up over here. Okay, let's go through another one here. So tangent of x plus y equals y, and that makes this really funky graph over here. So let's take our tangent of x plus y equals y. And we're going to take the derivative with respect to x of both sides. And I'm going to write this in a few steps here. So derivative of tangent. So tangents are outside function. So what we'll have is secant squared, and then we keep the inside the same. And then we're going to multiply, and this is where I'm going to kind of write it out in a few steps, the derivative with respect to x of x plus y equals, and over here we could go ahead and simplify, so that derivative of the function y, we would end up with a 1, but then we also have dy dx. Okay, so the piece I still need to simplify is this derivative with respect to x of x plus y. So we have the secant squared multiplying on. And then what we're going to have in here is, and again, I'm going to write out lots of steps here, but we have the derivative with respect to x of x plus the derivative with respect to x of y, all equals dy dx. So focusing on the derivatives in here, what we're going to have is that secant squared is still multiplying on up front. Derivative with respect to x of just x is 1, plus the derivative of y with respect to x will give us dy dx equals dy dx. So now we're done taking the derivative, and what I want to solve for is dy dx. So what I'm going to go ahead and do is distribute secant squared in here. So we'll have 1 secant squared x plus y plus secant squared x plus y times dy dx. And now what we want to do is, if you see dy dx on two separate sides of the equation, so like we have one on the right-hand side, one on the left-hand side, we want to group those terms on the same side of the equation. So I'm going to do is subtract away that secant squared x plus y times dy dx. So what that will give us is we'll have that 1 secant squared x plus y alone on one side of the equation, and then we'll have just 1 dy dx minus secant squared x plus y times a dy dx. Now why we want to do this is once we get them on the same side of the equation, we can factor it out, just like we would factoring out a variable. So we would have that secant squared x plus y on the left-hand side equals factor out dy dx, and we would be left with a 1 minus secant squared. And now what we can do is divide away that 1 minus secant squared. So when you have dy dx on both sides of the equation, get it to one side together, and then you'll have to factor it out so that you can divide everything else away. So that would leave us with dy dx equals secant squared x plus y in the numerator divided by 1 minus secant squared x plus y in the denominator. Okay, there's some of our first examples here. We'll get some more examples in the next video and some equation of the tangent lines, but that's our process for our implicit differentiation.